For our project, we chose to focus on combustion, which remains the main source of energy that humans use. It powers a wide variety of processes, including waste sorting, rockets, power plants, internal combustion engines, and it's an inherently thermodynamic process because it involves turning chemical energy into heat. So for our project, we chose to make a combustion-powered device, which is a marshmallow launcher, and analyze the reaction as it occurred.
We went into the machine shop to sketch up a simple prototype of our device, then went to Home Depot and purchased our materials, which were the PVC pipes, caps, rubbing alcohol, and a lighter.
Okay, so before we want to test out our marshmallow launcher, we want to make sure that the pressure buildup inside the tube would be within the limits that the PVC can handle. So to do that calculation, we first take into account the volume of our combustion chamber, which ended up being 0.3 liters, which goes to 0.013 moles of air. Air is roughly 20% oxygen, so that gives us 0.009375 moles of O2. And the stoichiometric equation for the combustion reaction here shows that there's a 2 to 9 ratio between the amount of oxygen and the amount of fuel you need. So the amount of fuel we were planning on using to get complete combustion ends up being 0.0021 moles of isopropyl alcohol, which is exactly 0.16 milliliters. And then to calculate what the pressure buildup would be, we were assuming to be conservative, that is constant volume, so that would get us our max pressure. You use the enthalpies of reaction or of formation of the chemicals involved to get the total change in enthalpy for the reaction, which is 3,659 kilojoules per mole. And since we're assuming in our system there's no outside heat transfer and the only components of the internal energy are the change in enthalpy due to temperature change, no kinetic or potential energy changes, the equation simplifies down to our change in temperature is the change in enthalpy for the reaction over the specific heat of air at 400 degrees Celsius, which is the combustion temperature of isopropyl alcohol. And so that gives us a temperature change of roughly 4,600 degrees Kelvin. And using the ideal gas law, you can come out to holding volume constant at 0.3 liters. We get to a max pressure of 250 psi. And so that's like the worst case scenario if the volume was constant. And we found out that it was very much within the limits of what our PVC could hold without failing.
In this section, we're going to show you how we got the velocity of the marshmallow at the end of the tube. So here we see 1 frame, 2 frame, 3 frame, 4 frame, 5 frame, 6 frame, 7 frames for the marshmallow to get to the beginning of the last piece of tape, which is 50 centimeters. We can use this information to find the velocity and acceleration of the marshmallow in the tube. Because we know that the iPhone records at 240 frames per second, if we do 7 divided by 240, this should be the time that it takes to get to the end of the tube. We also know the distance, and therefore we can find acceleration and velocity of the marshmallow.
So now I'll take you guys through our experimental analysis. We did this by first looking at the acceleration of our marshmallow. We did this by measuring the distance of our pipe and then finding the average time it took for our marshmallow to travel through the pipe, assuming constant acceleration. We found the average time to be 0.024 seconds, and thus our acceleration was around 1900 meters per second squared. We then found the force exerted on the marshmallow through that, and by measuring the weight of the marshmallow, the mass of it, we found to be 0.7 grams, and then we found our force to be 1.385 newtons. And then lastly, we found pressure through the equation of pressure equals force over cross-sectional area. We measured the cross-sectional area of our pipe through here, which is the same cross-sectional area of our marshmallow, and that area is 7.85 times 10 to the negative 5 meters squared. And thus we found a pressure differential of 2.56 pounds per inches squared, but that's not factoring in the atmospheric pressure of 14.7 pounds per inches squared. And so thus the pressure differentials of 2 led us to say that the pressure inside of the chamber is 17.26 pounds per inch squared.
All right, so we just want to talk a little bit about why the reality of our experiment was a little different than the analysis we conducted, which we assumed was occurring at constant pressure. There's a lot of factors playing a part in this. One is that the reaction rate isn't fast enough, so the marshmallow, begins to move through the tube before combustion is completed. The volume is not constant because the marshmallow is moving, so the reaction is occurring in a different space. We assume a constant volume when we calculate this. Also, the force is not constant as the reaction occurs and stops occurring. There's friction in the tube, obviously, and it's not a completely sealed system because we have the hole where we put the lighter. As such, our pressure increase was minimal, partly due to the nature of our experiment. Also, it illustrates how combustion is not completely efficient like any thermodynamic process.